Okay, so as I said, that structure of materials. So we looked at the structure of materials. Why is it important to study? Is because it affects the properties and structure can be engineered by process. So, since it affects the properties, it also affects the applicability. Okay. And structure, as we looked at, structure has various length scales. So, structure can be macro, it is micro, it is nano slash atomic, and then you have atomic slash electronic or electronic. Now, this is first is typically looked at by naked eye. Micro and nano or atomic structure, you have to go under the microscope. So, you go from optical to SEM to a TEM. This is the typical progression as you go from micro to nano structure. And then for atomic or electronic structure, you have to typically do simulations. Now, why are we interested in now this structure of materials is important, as I said, is from the processing and properties from the tetrahedron point of view, because structure is intricately related to properties, it is intricately related to process and the application. So, earlier we classified materials in 4 categories. That was, the first category was metal and alloys, metals and alloys. Second was ceramics and glasses. Third category was polymers and elastomers, and fourth category was composites. Now, basically we looked at the functionality in our classification. So, polymers, as we know, metals, they are strong, ductile, tough, but they have poor corrosion resistance, they have high thermal electrical conductivity. Ceramics on the other hand are brittle, but they are very strong, but they have low electrical thermal conductivity by and large. Polymers on the other hand are soft, light, they can be stretched to long distances, they are also tough and they are also very corrosion resistant, but they are not very good for high temperature applications. Composites on the other hand are manufactured in a manner so that you mix 2 contrasting materials to leverage the advantage of both the different classes of materials. Now, that is one way of classifying. Second way of classifying is these materials is on the basis of how atoms bond in these materials, because the properties of these materials and the structure of these materials are determined to a large extent by the way atoms are bonded in these materials. So, for example, metals and alloys are typically they are bonded via what we call as metallic bonds. Ceramics typically and glasses are bonded by ionic bonds or partially ionic covalent or covalent bond, largely covalent bonds. So, things like sodium chloride would be highly ionic in nature, bonding. Things like silicon carbide and zinc oxide, they will have partially ionic and covalent in bonding in nature. Diamond on the other hand will predominantly be covalent, or silicon will be predominantly covalent. Polymers on the other hand, they have a mix of covalent and secondary bonding. And it is the nature of these bonds which is very crucial in imparting the properties which these materials have. Metals have high electrical conductivity, high thermal conductivity, malleability or ductility because they are bonded by metallic bonds. Ceramics are strong and they have low electrical thermal conductivity, and they have low coefficient thermal expansion because they are bonded by ionic bonds or covalent bonds. Polymers on the other hand are soft, low strength because they are primarily there is a mix of covalent and secondary bonding, and the secondary bonding plays an important role in determining the properties. So, we will briefly look at first the bonding aspects of various materials before we get on to the atomic structure of materials. So, let's begin with what we call as bonding. It's not a full course on bonding, it's just the primer on bonding. So, we know that you have atomic structure. So, depending upon the atomic number, you can have a nucleus, and this nucleus has protons and neutrons, and surrounding this you have various electrons. So, you can have, depending upon the type of, so 1s2, 2s2, 2p6 and so on and so forth, depending upon the so if you have, let us say 10, Z is equal to 10, you will make a structure 1s2, 2s2, 2p6, and as you go higher you can keep building the atoms. So, basic and atomic mass of a material of an element is equal to Z, which is the atomic number, plus N, which is the number of neutrons, right. Okay. So, this is the atomic mass. So, these are two things as far as we know about the atoms, and atoms, we have to know these things about atoms because everything is made of atoms. So, atomic structure has to be understood well before you go into bonding. So, and also we know that that electrons in atoms, what are the characteristics of electrons in atoms? The energy levels of electrons are, you can say, discrete or quantized, right. So, there are specific energy levels which electrons occupy, and as you keep filling the metals, an atom with an electron number of electrons, the tendency is to occupy the lowest energy state first, and as the lowest energy states are filled, then the higher energy states are filled. So, for example, you can have n is equal to 1 state, this is the E1, and as you go to n is equal to 2, you go to E2, and as you go to n is equal to 3, you go to E3, and this is basically increasing energy, right. So, that is why you will see hydrogen atom with 1 electron will be at the lowest energy state, and as you keep adding electrons to helium, to sodium, potassium, carbon, and sodium, potassium, iron, and so on and so forth, you will make it, you will go higher up in the energy of electrons. And of course, as far as atoms are concerned, there are atoms with partially filled shells, configuration, and then you have completely filled, right. So, completely filled, what are the examples? The examples are helium, neon, xenon and krypton. These are all, these have completely filled, that is why they are called as inert gases. Okay. In other atoms, the electronic shells are not completely filled. For example, if you look at iron, okay, iron has atomic number of 26. It makes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and what do you have then? 3d6. This D can have 10 electrons, but it has only 6 electrons. It is partially filled. Now, depending upon what you mix iron with or how iron atoms are present, there is a tendency to give away these electrons or take the electrons. That tendency to give away or take the electrons is called as electronegativity or electropositivity of atoms, which is what is going to determine what kind of bonding they will have. Or sometimes what happens is that they do not necessarily have to give away the electron or to take the electron, they can share the electrons. So, depending upon how the electrons are configured or shared between the atoms, they undergo certain kinds of bonding. So, as we can see that except inert gases, all elements have unfilled electronic orbitals, right, and as a result they are not stable, they are unstable, which means to be stable they have to have a stable configuration. So, what should they do? They should do something with these electrons which are unfilled, which are incomplete configuration of electrons in the outer shells. They have to be taken away, they have to be given away, or they have to be shared. Something has to happen, and that is why these are called as valence electrons. Valence electrons. These valence electrons are, or you can say these outer shells, these are the outer shell electrons which are not completely, which are not in the number of, which are not equal to the number of total number of electrons that particular orbit can have. So, so if you look at the periodic table now, so I do not have periodic table here, but if you look at the periodic table, you have various columns in the periodic table, right. So you can have 1A, you can have 2A, and after 2A you have 3B, and then you have 4B, 5B and 6B, 7B, followed by then you have group 7 all throughout. So, this goes group 7, and after that then you go to 1B and so on and so forth. So, on the extreme right what you have is the inert, right. On the extreme you have inert, which is called as 0, and all the way to here we go to 7A. 7A is nothing but the halides just before the, this is, so as you go from left to right of the periodic table in terms of number of columns, on the left you have elements which are called as electropositive. On the right, just before the inert elements, you have elements which are called as electronegative. And what is this specific thing about electropositive elements? Electropositive elements are the elements which have tendency to donate or to give away their extra electrons, which are basically the incomplete shell, incomplete number of the extra electrons which are lying in that shell. And these electronegative elements have a tendency to accept. So, things like sodium, potassium, magnesium, calcium, all these elements on this side they are electropositive, they tend to give away the electrons. On the other hand, things like chlorine, fluorine, bromine, iodine, they have a tendency to accept electrons. Similarly, you have, if you go to 6A, if I remove that, then you have oxygen, sulfur and so on and so forth, they have tendency to accept electrons. So on one side you have atoms which have tendency to donate the or give up the electrons. On the other side you have atoms which have tendency to accept the electrons. In the middle you have atoms right up to the column 3A, right up to the boron, aluminum, you mostly have elements which will tend to give away the electron. So on this side you have electropositive elements, on this side you have electronegative elements, and when you mix these elements with each other you form bonds, because one has a tendency to give away, another has a tendency to take, and that is where the bonds are formed. So typically electronegativity ranges, so this is determined by the nature of electropositivity or electronegativity is determined by a value called as electronegativity, and electronegativity ranges from 0.7 to 4. So 0.7 will be electropositive or less electronegative, 4 will be highly electronegative. So for example, if I look at lithium, this is denoted by a parameter called as chi. So for lithium this value is typically 1. I will give you some numbers. For sodium it is about 0.9, for potassium it is about 0.8. Okay. If you look at the column 2, magnesium is about 1.3, calcium is about 1.3. If I go a little further, then titanium has a value of about 1.5, zirconium has a value of about 1.3. If I go further right, then I have, let us say, chromium. Chromium has a value of 1.7, manganese has a value of 1.6, iron has a value of 1.8, and your cobalt has a value of 1.9, copper has a value of 1.9. You can see that most of these elements have electronegativity which is slightly on the lower side, starting from lithium which starts at 1, it goes right up to about 2 for most metals. Okay. So they are in some sense strongly electropositive or moderately electropositive. So these are, so you can say a point, so let me just define here, this is strongly electropositive, this would be strongly electronegative. So these are typical metals. Now if I go to other classes, other side of the periodic table, you start from fluorine. Fluorine has a value of 4, chlorine has a value of 3, iodine has a value of 2.7, oxygen has a value of 3.5, sulfur has a value of 2.5, nitrogen has a value of 3, phosphorus has a value of 2.2, carbon has a value of 2.5. These are strongly electronegative, and these elements make compounds. That is why you see in nature a lot of things appear as carbides, nitrides, oxides, sulfides, iodides, chlorides, because these elements are ready to react with other elements in order to take their electrons. So this is the basis of distinguishing between the atoms. So based on these parameters, you have excess number of electrons in the outer shells, or there is unstable configuration which allows metals to do something with these extra electrons so that it becomes a stable configuration. They tend to form bonds, okay, and these outer shell electrons which are not sufficient number, they are called as valence electrons. And how they react, how these different elements combine with each other, it depends upon the differences in the electronegative. So, if you have a heterogeneous material, in a heterogeneous case they will have to they form bonds because there is a tendency to accept and give the electrons. But if you do not have heterogeneous compound, for example say iron or say only copper or say only aluminum, in that case there is some other mechanism of doing something with those electrons. So, this is where we come to bonding. So, bonding is determined by how electrons are basically valence electrons, okay, how valence electrons are handled by atoms when they are assembled together. Okay. So, you have two cases, you can have heterogeneous mixtures, more than one element, and you can have single element. Okay. So, for example, this would be mean basically you can say compounds, okay, not heterogeneous, but I would say compound. So, for example, things like sodium chloride, zinc oxide and so on and so forth, and here it would be anything which is single like iron, cobalt, nickel, aluminum. Okay. So, let us see what different kind of bonds are. Now, before we go into bounding, we need to understand the fundamentals of what happens when you put the atoms together, and that is that you can understand by understanding the interatomic. So, this I am covering very fast because this is not the basically basis of this course, but you must know this, that is why there is a recap of this particular interatomic forces in. So, when you bring two atoms together, these atoms are located at a distance r, which is the equilibrium distance. And why is this equilibrium distance, what is the significance of this equilibrium distance? Because when you bring these atoms together, the forces between the atoms, let us say force F. Force F, there are two kinds of forces, first is the repulsive force, second is the attractive force. So, this is let us say Fr, this is Fa and this is the distance r. The stable configuration is the configuration where the net force is equal to 0. So, this is let us say let me just write it with a different color. So, this is the stable configuration. A stable configuration is at a distance r naught at which the force is equal to 0. This is 0 value. Okay. Correspondingly, you can plot what we call as the energy, the potential energy, let us say E, potential energy. This potential energy at this particular point should be minimum, right. So, if you plot the potential energy looks something like that, okay, and this is the distance r naught at which you have a potential energy which is defined by or E naught or W naught depending upon how you, in this case we can say just E naught, and this E naught is called as the bond energy. The distance, the energy corresponding to the equilibrium distance between the atoms is called as the bond energy. So, this potential energy can be given as sum of a repulsive term and sum of an attractive term. So, this is given as A prime Z1 Z2 E square divided by R plus B divided by R to the power m, where m is a constant. So, this is a negative term which is attraction, and this is a positive term which is repulsion, and this is where, so at some R you minimize this E, which is what gives you the bond energy. So, what we will do in the next lecture is we will look at different kinds of bonds in the materials, and then we will move on to the structure of materials. Any questions? Okay, thank you.